solve the Navier-Stokes equation for Newtonian fluid. Let's get start the video. This is the final form of Navier-Stokes equation. We can also write it as how we can solve plus simplification. We take a stress matrix, tensor matrix. The diagonals are the stresses and the non-diagonal are the shear deformation. Let's get start with the diagonal elements stresses. We can also write it as sigma xx partial u upon partial x. Similarly, for sigma yy we can write it as sigma zz. We can write it as partial w upon partial z. In this matrix, these three diagonal elements are the stresses, and the also six elements are the shear deformation. These 1, 2, 3, 4, 5, 6. We can also write it as sigma xy, which is equal to sigma yx. We can write it as similarly for xz and yz. Newtonian fluid stresses is directly proportional to rate of deformation. Tar xx we can write it as similarly tar yy we can write it as similarly we can take a stress tensor matrix. We can write it as sigma xy, which is equal to sigma yx. Similarly, xz is equal to torque zx. Similarly, we can write it as how we can write it as for x component, velocity component is u. We can partial u upon partial y, and plus for velocity component for y is v and partial v upon x. Here we can write it as for stress tensor for x component velocity is u partial u upon partial z, plus for velocity component for z is w, and we can write it as partial w upon partial x. Here we can same it is write it as partial velocity component for y is v partial v upon partial z, plus partial the velocity component or the z is w partial w upon partial z. As we know the momentum equation for three dimensional, we can write it as rho du upon dt. This is material derivative is which is equal to minus partial gradient of p plus gradient dot torque ij plus rho g. For compressible fluid, divergence of v is gradient of v is equal to 0. For x component, here we take this momentum equation for x component. Okay, we can write it as rho u du upon dt, which is equal to, here we can write it as for x-axis we can write it as rho p upon x, plus here we can write it for x-axis, here we can write it as rho gx. We can put the values of txx as we can write it here. We can put the values of txx, tyy and tz. From this we can write it as a txx value, and we can put the value of tyx from here. Tyx, we can put the value of tyx, and similarly for gx plus rho gx. For constant viscosity, we can take is viscosity is constant. We can write it as we can write it as rho du upon dt, which is equal to rho v upon x partial x plus 2 mu partial square upon u partial square u upon partial x square plus, similarly we can write it as here we can divergence of v is equal to u is equal to 0, and we take it as constant. We can write it as here we can multiply by both, which is equal to partial u upon partial u square over partial x square. We can write it as similarly we can write it as we can take it as constant. Here we can take it as constant. Simplification of Navier-Stokes equation from conservation of mass. Conservation of mass equation, we can write here. We can simply we can write it as we replace it as partial u partial upon partial x and partial v upon partial x. Here we can get it as name equation number a. From continuity equation, we can conservation of mass. We can write it as we can calculate the value from here and put the value it is here. Putting the values, these value in equation a. Equation is here. We can put the value is here, which is write it as here. We can multiply these, and these two terms are cancelled with each other. We can write it as here. And similarly 2 mu, and which is here, these both are minus, which is here. So we can write it as take as common as mu, and u is common here. We can write it as gradient square. Now we put the value here. We can also write it as rho du upon dt, which is equal to minus rho p. Here is p upon x plus here and gradient square u plus rho. This is the Navier-Stokes equation for along x direction. Final form of along similarly for y direction, we can write it as here y, and the velocity component is v. Similarly for z, we can write it as here. So we can also in vector form, all vector form, we can write it is here. This is gradient p and the final form is here.